in the comments. And the title will be posted by Gregg.
Thank you. Okay, so my title is Conjectural Equivalence between two categories of G modules. Is that large enough? So this is joined with Penkov, some of you may have wondered what was Alexei referring to the other day. In his talk, he was talking about some joint work of Penkov, Zuckerman, and myself. That's very much the same philosophy as what I'm talking about today. But in fact, that work is geometrical and uses D modules, whereas this work so far is purely algebraic. Pretty vague title. It's partly a send-up of an old paper by Bernstein, Gilfun, and Gilfun called On a Category of G Modules. I think it's one of the great titles in representation. Of course, that category is now called Category O. So I should say that a classical category is O, which actually depends upon some choices. So you start with semi-simple Lie algebra, Brill subalgebra, and a Cartan subalgebra of the Brill subalgebra. And then you attach a class of objects to this data. And probably most of you know, but I'll just say very quickly, so that we're all on the same page, that you want your G modules to be finitely generated over the enveloping algebra. You want every vector to generate a finite dimensional D submodule. And you want H to act semi-simply. Now, of course, since H is a subalgebra of D, and D is acting locally finitely, H acts locally finitely. And so then asking that H acts semi-simply is the same as asking that H acts diagonalizably in the module. This is an awfully lucky guess on the part of BGB, because this category turned out to provide many people with employment for the last 40 years. And it's still a thriving industry. So I'm certainly going to try to build on what they did, but in the process I'm going to have to leave category all behind and work in a much larger category, about which less seems to be known. But I'll try to motivate the necessity of enlarging the category. All right, so I want to write down one or two more things on this whiteboard before I go to the report. Another classical category well, right, it's MGK. And here, K is the symmetric subalgebra. So again, G is semi-symmetric. And for now, what I'll mean by this category is G modules, which are locally finite with respect to K. I could impose further conditions, and I'll come back to that. Again, Gelfand and his school considered certain natural subcategories of MGK. And it was apparently important problem to describe these categories in terms that we now call the theory of quivers. But I won't dwell on quivers today. All right, so these categories, in fact, both get mentioned in Gelfand's talk to the Nice Congress in 1970. Who here participated in the Nice Congress? No? So,
72, I think.
sorry?
72.
I believe it was 70. We're having a lot of difficulty with our memory base. So we'll discuss it. Yeah, so
you're right.
No, it should have been 70.
It was 70, yes.
And probably the proceedings didn't come out until 70. So there's a famous paper by I and Gelfand. Nice, ICM. And I'm going to go out and assert that it was 1970. One interesting point is that, of course, in the tradition of the Cold War, Gelfand was not granted permission to show up and give the lecture himself. So the lecture was given by my then Professor Dan Moscow. All right, so the first basic question that you could ask is, well, two categories. I'm saying TWO. There's no pun on higher category theory. If two categories appear naturally in a context, there ought to be some way of relating one category to the other. In fact, this has been a very fruitful idea. You can go in both directions. You can try to start with an object in GK modules and go to an object in category O, or you can try to start with an object in category O and then go to an object in GK modules. But of course, what does it mean to go to another object?
So for GK, do you make any semi-simplicity assumption? Or?
Yeah, so of course, in order to say anything reasonable, I'm going to have to introduce the technical idea of semi-simplicity with respect to K, which is really only a condition on how the center of K acts.
Sure.
So, let's take this to be the introduction. And I should start with the article.
Yeah.
Sorry?
I think you should start with the board on the back.
Start with the word on the back.
That's what I would recommend.
Okay.
Well, neither work really well.
It doesn't matter.
Next time I'll bring my viewer. Alright, so let's consider a diagram. So let's consider that I have a diamond of algebras. So the main pair are subalgebras of G. And as before, we'll take B real subalgebra. Okay. And now I'm not going to restrict myself yet to the symmetric case. So take A to be a reductive of G subalgebra. I'll need to justify going to this greater generality, but I hope that quickly you'll see the point. And then T will be part-time subalgebra K. Then I'm going to write CGT is going to be the category of GT levels that are semi-simple. Now let's keep in mind, so that I can make clear how my assumptions relate to the assumptions of other talks. Not assuming that K has the same rank as G. All I know is that the rank of K is less than or equal to the rank of G. So that my T is not necessarily a Cartan subalgebra of G. So I should actually take that into account eventually. But to drive home the ultimate simplicity of the idea, let's not choose a Cartan subalgebra of B quite yet. We'll do that. So that I'm not immediately. Then I'm going to write CGK is the analogous category for K. Now, another thing that I want to emphasize is that there are no algebraic groups yet. This could all be embellished by writing down the corresponding diagram of algebraic groups, and then I would have a notion of a CG Roman T module and a CG Roman K module. But for now, in the interest of exposition, I'm just going to start with these potentially very large categories. So then, it's not quite clear how D should work into the discussion here. The first thing that one can do, even before a choice of D, is one can consider a functor which I've been writing gamma kt and it's the adjoint functor to the inclusion. Put in a more down-to-earth way, you take a GT module and you look at the largest submodule, which is K locally finite. This functor, I ain't really credit to Hodge. I believe it's implicit in this paper on holomorphic discrete studies. The difficulty is that Hodge was immune to the language of categories and functors. So he talked about this operation as an operation on modules without also discussing operations on morphisms. I really want to think about this as a right adjoint. So, our genre
Well, Hodge surely introduced grammar modules.
Yes, that's of course another point that I was going to make, yeah. I mean, the naming in this subject is, as usual, quite inaccurate. I'm not going to call this a Hodge functor in deference to Hodge, who would probably blanch at the name. Alright, so this construction was actually around for a long time. It can be used, for example, to give an algebraic description of the principal series of a semi-simple Lie group. And so I'll just mention that without going into any details. If you look at Dixon, starting with the process and writing Dixon built me all this. This functor appears quite early in the book and gets repeated over and over again. Perhaps not the relative functor, you might have just considered the case where T is 0. But certainly the idea is in the literature. And the idea which I was somehow led to introduce in the late 1970s was the idea of examining this functor in the language of homological algebra. So at first it's just a functor between the categories, but because I'm working with a sufficiently large category, I know that there are sufficiently many injective objects in the domain category. CGT has, I'll say, resolutions by injective objects. And this is already where category theory is playing a role, because I'm not resolving by injective G models. The injective G models are not in this subcategory. They don't have any local finiteness with respect to G. So what I'm talking about is objects in CGT which have the injective property that you learned from or from Beer. Is that the correct pronunciation? B-A-E-R? The German algebraics. Alright, so because of the possibility of injective resolutions, I can then introduce the derived functors again. This right adjoint functor is also left-hand side. And so then I can introduce the functors which go from graded GT models to GK models. And how are these calculated? You take an injective resolution of a GT module within the category CGT, and then apply the functor gamma. That gives you a new complex, which can now have cohomology. Cohomology, but complex is by definition up-isomorphism R star gamma applied to an object. So let's just write down the formula to have as a comparison. So we're saying that G is the CGT as an object. R star gamma KT on B is by definition conforming to the cohomology of gamma KT I dot, where I dot is the resolution of B. Now this certainly doesn't look very computable. And I'm still asked, what do I need the T for? Why not just do this at the level of, going from G modules to GK modules? Because back in the old days, I didn't feel like I had to explain anything. But now, I'm a little bit more generous with these ideas. The point is that let's consider what happens if we apply this functor to the trivial module. So, should I be raising this, or is this? Okay. Alright, so here's sort of the first result. If you take R star gamma KT and you apply it to the trivial module, then you get T with trivial coefficients. And then this is something that both algebraists and geometers love because it's the homology. And now I will briefly introduce algebraic groups. It's the homology of complex algebraic group associated to K divided by the complex algebraic group associated to T. And that's, of course, a very famous topological space. It's a complexification of a compact Taylor manifold, which is one of our favorite manifolds that we learn about at LV. Okay, so that says that there's a great deal of structure for the answer when I include the T in the theory. That's as compared to the answer if you don't include the T. In this case, as you would expect, you get the homology of K itself with complex coefficients. Well, I never hear anybody talk about this space anymore. I mean, this was a popular space at one time. You know, the calculation of the homology of the Lie was a very important problem 50 years ago, 60 years ago. But I think somehow in more recent times, this is some more significant space. Alright, so what I've done here is I'm showing you that this theory of derived functors does produce non-trivial higher derived functors. Doesn't answer all questions, but it gives you the first indication that you're dealing with a functor which is certainly not exact and has interesting homological properties. Alright, so this is all well and good, but kind of cries out for input. So the input should be a choice of GT for which the derived functors are computable or related to something computable. And now the important thing to understand is that whereas in these very simple examples, you're just getting complex vector spaces, maybe with a ring structure. In general, you're getting a GK module. So this is not a typical cohomology theory from geometry. This is a theory that's a little bit more like a theory of direct images of sheets under maps, where you're really not passing directly to the cohomology of the sheet, but you're getting another sheet on another space. So I want to emphasize that what does it mean to say that I get an interesting answer? It means that I get an interesting answer. So the goal, now I guess I should. I realize that I'm putting at least half of me to sleep. I'll let you know when I wake up. So the goal is to find GP model V And interesting. She came up. Well, in the original application of this theory, I was very interested in the underlying Harshauer modules for the discrete series. So, to greatly oversimplify the history, consider the special case. Okay, so that's an angle, right? And G. And then T equals H. A part-time circle. Okay, and then, trying to state this as a theorem would require a fair amount of notation, but the point is that given d lambda and Harshauer's discrete series, there are natural choices. Of GT models. Let's call them M lambda.
What is D lambda?
Sorry?
What is D lambda? I mean, I can't quite read. Harshauer's.
Harshauer's discrete series.
Oh, the module.
The module, yes. Yeah, so infinitesimal discrete series. So I'm choosing a weight for H with some appropriate integrality and regularity. And
And of course, I never wrote down representation.
never wrote down the representation, but he
constructed the counter.
But, okay. As I read discrete series 2, at some point, he actually discusses a Harshauer module, which eventually becomes that module whose character is already constructed. That module that he writes down lives inside of the Schwarz space. It's not very well described inside the Schwarz space, but it's there. It depends upon some arbitrary choices, but it's there. So that's essentially what I'm addressing. Since this is just an example, I'm not trying to write down the theory. What we've seen that the discrete series now is thought of both analytically and algebraically. And by this d lambda, I mean the algebraic module, which is at least implicit in Harshauer's second paper on the discrete series. So let's say discrete series GK module. So there are natural choices of GT modules. Well, let's make this a singular. Again, to avoid such that d lambda is isomorphic to Rs gamma k t m1 where S is half the dimension k1t. And that is, by the way, an integer under the hypothesis, because T is a Cartan subalgebra K. And Rj and KT and lambda is equal to 0 for J is not equal to S. Okay, so the full theorem is certainly stated carefully in many places. I think I stated it correctly in a lecture at Columbia some years ago. So the point is that this is a kind of paradigm for the problem. I want to understand, well, then I can construct other interesting GK modules. Possibly in the case when K is not symmetric, by making an appropriate choice of GK module. Are there any questions so far? Alright, so the idea is that I would like to skip ahead to 2014 because I've already used that a lot of time. So the new theory, coming almost 40 years later, this is around 1977. Find categories, or find subcategories of CGT for which R star gamma AT restricted to the subcategory. And I think I want to word for which. Yields interesting subcategories of CGK. So this is going quite a bit beyond the original example of discrete series. But I'm still in many ways motivated by what seemed to work back in the 70s. So I have to describe what's a natural way to build some interesting subcategories. Well, I've kind of hinted over here that one should use a Borel subalgebra, which is naturally part of the problem. So let's go back to this. Let's go back to this guy. Well, if I simply ask that B be a Borel subalgebra of G that interpolates between T and G, it's not a very strong condition. In general, T is not a Cartan subalgebra of G, and there are going to be many Cartan subalgebras of G that contain T and that lie in So I really should draw more extended picture here. Should go with G and K contains T, and then this picture then H is the Cartan subalgebra of T. T is the Cartan subalgebra of K. As I said before. So there's some flexibility here. If I take right, M B is an object. In this Gelfand category, Bernstein-Gelfand category, then I can consider R star and gamma AP. And B. The reason why I'm keeping the B in the picture is that it's a variable. I haven't necessarily chosen B yet. So what sort of properties could this have? Well, what Yvonne and I discovered about 10 years ago was that there's a very nice class of Borels where you can say quite a bit about yes. So, join you introduce the notion of an idea of D is compatible with T. And the definition is that if there exists is an element H in T such that B is equal to the parabolic subalgebra G naturally associated to this semi-simple element T. So let me just say that a little bit more slowly. So since K is acting reductively in G, the T consists of semi-simple elements. For G, and pH is the parabolic subalgebra. Term wave. I can think of H as now an element in scripting. So that I can think about it either in terms of roots of H or weights of T. Alright, so there's a well-defined procedure here. And in this case, we're getting a rather strong restriction on G. So what is the consequence of the restriction? So let N be now any object in this category associated with this particular H. And I get that RJ gamma TT of N has finite type. Even rather than using that technical term, has finite K multiplicity. Alright, so by construction, the derived function module gives a GK module, it's semi-simple over K. But it's not obvious that it has finite multiplicities. And this additional condition guarantees finite multiplicities. Now, there's one slight problem here, and that is that T may be so small that it doesn't contain any regular semi-simple elements. Well, if that's the case, then we look at a piece of H, it's possibly not of realm, but we can assume that it's minimal relative to this condition. I think it's easiest for the purposes of this talk just to consider the case where T is regular in G. So otherwise we're talking about parabolic category O, which is one of the sub-industries of the category O industry. We probably need another talk on that. Alright, so the fact that we get finite K multiplicities is a good sign. Now we should also talk about where does this J live? Well, it was a general fact that if J is greater than the dimension that came on T, then RJ gamma AT n is 0. It's a little bit surprising at first because first we're doing homological algebra with T. But the answer for the homological dimension only depends on K. Now in the symmetric case, this dimension tends to be rather large if the dimension of G is large. But we're not requiring anymore that K is symmetric. K could be as small as subalgebra isomorphic to SL2. So let's just write down what the result looks like in the SL2 case. Alright, so I realize that several people here worked on the derived functor construction in the Horace-Chandra model case, and I'm not mentioning you by name. So maybe I should just say Wilfred and Pablo certainly they have made fundamental contributions in the Horace-Chandra model case. Wilfred also succeeded in relating this derived functor construction, as it's called for no good reason, to the Bernstein-Davidson classification. But I'm not qualified to state that term. So what about that? Alan? Oh, alright, so let's talk about an example from the last 7 years. This has been a long and strange project. That is, assume that K is isomorphic to SL2. That means that I could be talking about a symmetric case, but there aren't too many examples where I can talk about. SL3, SL2, and I can talk about SL2, SL2. So I'm writing down pairs, G and K, and if I understand the classification, these are the only symmetric pairs where the K is isomorphic to SL2. Strictly speaking,
Yeah, the second case is a GeoGebra.
Strictly speaking, one should come in GeoGebra. Yes. But our work, where we're assuming that K is isomorphic to SL2 is relevant to this symmetric pair. Okay, so what do we get out of the proposition? In the opposite order. RJ, M, KT, and is equal to 0 if J is greater than 2. And again, what is the n? The n is module which behaves nicely with respect to the Cartan subalgebra of K, which is not one-dimensional. So it was generated by a single semi-simple element in G. And so in fact, I don't have to make any further assumption on n here. But then in the first case, I have that R, J, M, K, T, N. That's finite SL2 for J equal to 0, 1, 2. And that's now under the condition that n is in this much smaller okay. Remember that my category here is a kind of a fictional category where all I'm doing is assuming semi-simplicity with respect to t, but there are no finiteness conditions. Now here I'm assuming that my n is in the O category. And this H is basically the centralized little element H to G. Alright, so I started at quarter
Plus 2.
Okay. Alright. So let me try to formulate a conjecture. These examples, of course, do not exhaust possible examples. So I could also consider the principle SL2 and G. So the conjecture is for a computable constant n in natural numbers. Let's write let's now write C G B bar T N in the category of GT modes. And the additional conditions that I have in mind here, that these are B bar terrible. A semi-simple. There's still T semi-simple. And the spectrum of H in N is bounded from below. But technically N plus 2. Then I restrict my derived functors to the subcategory. That actually doesn't require anything more than that N is possible. But the more crucial thing is that one PT from C, G, E bar T, N to modules with finite handling. Is an equivalence with this image. Now we actually have conjecture about the image, but possibly I've used it by time. So thank you very much.
Question?
Well, comment maybe. Comment is that we understand very well the simple objects in the image.
Yes.
And those are precisely the GK modules whose minimal K-type has highest weight. Because the minimal K-type is now an SL2 representation. So its weight is N or higher. So, but if you compose the GK module over SL2, it just becomes a finite sum of.
Am I allowed to write this down?
This is my comment, that's a comment.
Oh, okay. So that's simple and then the image. Then the lowest K-type, lowest SL2 element. And conversely, if S is simple and has two type greater than or equal to n, that is in the image. I'm forgetting one thing here, and that is that one should restrict the weights of t to be integers greater than or equal to n plus 2.
Yeah.
Any other comments or questions? Yes?
Can you say some examples of what is meant?
Yeah, what's the bound on n?
Yeah. Okay, so,
The word computable then.
yeah. Okay, so we actually estimated it in a recent paper. That maybe gives you the opportunity to plug the alternate station. So by that I mean, there seem to be two stations coming out of Boston. There's the Schmidt station and the Logan station. And so the Logan station, I think that they're both observing FCC rules. So there's a site called leadgroups.org. And you go to papers. And you'll find 3 papers that are joined between Yvonne and me. So, and they're called the papers on what we call generalized corresponding models. One is based on lectures that I gave, looking around for my 2 students from 2009. So I can give lectures here at Jacobs on generalized Harshadra models. So they now appear on this leadgroups.org site. The most recent paper actually tabulates an estimate for n in the case when g is simple. It's still an interesting problem to extend our methods to semi-simple g. Nowhere in the problem as I formulated it do I need to assume that g is simple, and in fact, this is a great example. Or however, we know that the n has to be 1. So let's see, in the case of examples on the board, which are classic, and I'm cheating a little bit, but in fact, if I take the root as L2, then anything which is a finite type for this pair is automatically a finite type for SL3 comma GL2. So in this case, we make a little table. The n here is 3, and here is 1, and here is 1. And if you look at the classification of modules for this pair, you will see a vast simplification. And you notice that you're throwing out a lot of modules by assuming that the lowest SL3 type has the highest weight at least 3. So it shows that when we go back to the classical theory, there's still a huge gap. We have not offered a new classification for this symmetric pair. Things look a lot better for these two symmetric pairs, but still, we have to exclude the case of eddy is 0, which looks kind of strange. But of course, for these pairs, the Harshanga models have been known forever. So I think in terms of examples, those three symmetric, or nearly symmetric examples already give you some indication. And then the one example which began this whole project back in something like June of 2007. So this is a non-symmetric example. Take G to the S4. 4x4 symplectic matrices. And then you take A, you have a principal SL2. And in this case, you have to have N greater than or equal to so in other words, you have to go to the 6-dimensional representation. And here is surprisingly a lot known, and is also surprisingly a lot known, not understood at all for this particular pair. And it's good exercise for graduate students to figure out which SL2 I'm talking about. I mean, I use some fancy term, but you can write it down in matrices.
Any other questions?
So, I have such a question. So, you prove some theorem for, say, pairs GSL2 or something of this sort. Is there any analog for them for the Harshanga case? So, you could say that you could fix some semi-simple element in K and produce kind of similar two categories of just parabolic kind of analogy of a category O with weights which are bigger than some number, and GK models with minimal K type which is bigger than some number.
I would say that Yvonne and I are thinking about that. We need to consider your question. The fact that we're looking at K isomorphic to SL2 is an indication that what we're doing is very primitive. Now I realize I'm making a bad pun because it seems to be a reference to Wilfred's talk on primitive homology.
Well, I think
You have the definition of the SL2 acting on the Taylor calculus?
I think we should thank the speaker again.